Okay, so welcome to the introduction to rationals. We're going to kind of take a look at the behavior of these rationals, and we've already kind of studied some of the stuff, but let's kind of take a look at some of the important aspects of it. So first of all, what a rational function is it literally means a fraction, right? There's an expression on the top and an expression on the bottom, and it really means a fraction. So one of the most important things that we have to identify is we have to identify the domain. Like what numbers are in the domain? So first of all, we can say, well, all real numbers are in a domain, except certain numbers are going to cause problems in rationals. And where we need to identify the problem here is in the denominator. Okay, so in the bottom of these fractions, the denominator, that's really where we're going to be running into trouble. Okay, so first of all, we need to think about undefined. So what the term undefined mean is how can you have one slice of pizza if you don't have a pizza? Okay, so that's one easy way to think about it, right? 1 over 0, this does not exist. This is called undefined. It's an undefined math term. Okay, so now how to determine where something is undefined is I could say, let's set this bottom equal to 0. And then if I solve plus 7, I'm going to get x equals 0. So 0 makes the bottom of this, or 7 makes the bottom of this fraction equal to 0. Okay, so what you can really say here is that x cannot equal 7. Okay, you can put in any number you want, but it cannot equal 7. All right, so we're going to follow through the same sort of strategies here. So if I look at this next example, I'm going to say, well, set the bottom equal to 0. And then I'm going to solve. Now this is a dots problem, okay, so I'm going to say, well, x minus 8 and then x plus 8 is equal to 0. So I know two things that are true to make this equal to 0. Well, x minus 8 equals 0, so I add 8 to both sides, and I've got 8. Or x plus 8 equals 0, subtract 8, and I've got x equals negative 8. So what you can say about this function is that x can be any number except x cannot equal 8 or negative 8, because that's what makes a function undefined. So that's using the dots method. And on the third one here, we've got 6x minus 36. We know that this cannot equal to 0, okay? Negative 9 is actually okay over here. 5 is okay over here. Okay, we're only concerned with the denominator. So if I solve for this, right, I'm going to add 36 to both sides. I've got 6x is equal to 36, and then divide by 6, and then we're going to get x is equal to 6. That means 6 makes it 0 on the denominator. So x cannot equal 6. It will make this function undefined. Okay. Third one is using sum product. Okay, again, we could substitute 9 in here. That is okay. 9 and 0 on the numerator is fine, except on the denominator it's not. So what I solve for x here, we're going to use sum product. So we've got x plus 7, x plus 6 is equal to 0. So I know that x cannot equal, most of you figured this out by now, but x cannot equal negative 7 or negative 6. So if you're not sure, just set it equal to 0 and solve. Right? X is negative 7 here. And then what happens over here? Subtract 6 from both sides. X would be negative 6. So we can say, well, x cannot equal negative 6 or negative 7. And then there you go. That's what makes the functions undefined. So undefined is a key term when we're dealing with rationals, right? We don't want to substitute those values in. So what happens graphically is what is called an asymptote. An asymptote. So if we take a look at the first one, 45 over x minus 7, if I go to graph that in the calculator, right, you can see I got that on the top, 45 over x minus 7. If I go ahead and take a look at the graph of that, what happens here, you see a vertical line at 7, right? If I go down, 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 it'll go down forever, but it'll never touch. And it jumps up to the top, but it never touches 7, right? You can see it'll get closer and closer and closer to x equals 7, but it will never touch 7, okay? So now, if I take a look at the next one here, I go ahead and take a look at the next one here, x minus 5 over x squared minus 64, 8, and negative 8 were the two values that did not work. So if I go ahead and look at the graph, look at 8. All right, look at 8. See if I go right here and go up, 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 up. Look at the x value. See how it gets closer and closer and closer. Whoa, see if it jumps to get closer and closer and closer to 8, but it won't touch it, okay? So if I touch the asymptote here, if I go on the actual asymptote, you can see there's no y value. It doesn't exist, okay, in the top left-hand corner, right? And the same thing is true for over here. If I look at negative 8, right, if I zoom in, it'll never touch negative 8. If I zoom out, you can see those are asymptotes here. So rational functions usually have asymptotes somewhere, okay? All right, let's go ahead and take a look at the third one, right? So we know that this one right here, x cannot equal 6. So if I go ahead and take a look at the graph, right, there's an asymptote at 6, right? It'll never touch 6. If I go down, 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 down forever, it won't touch 6. And then if I go up, 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 up forever, it won't touch positive 6, okay? And then the last one right over here is I look at this is y equals x minus 9 over x squared plus 13x plus 42. We know it's the values that cannot work are positive 6, or sorry, negative 6 and negative 7. So if I look at the graph here, there they are. There's asymptotes at negative 6 and then negative 7. Okay, and if I scroll up here, the graph does something weird. Look at what it does. It kind of like comes down and turns around and then comes back up. Okay, it's just going down and up. It's like kind of sandwiched in between these two right here. So if I look down here and I go down and around, you see it kind of just bounces, but it'll never touch negative 7 and it'll never touch negative 6. Okay. Right now, you also might notice another asymptote in here, but for now, just focus on the original asymptotes, which come from the undefined terms, right? Which come from, well, x can't equal negative 7 here because it makes the bottom 0. X can't equal 8 or negative 8 makes the bottom 0. Can't equal 6, and then can't equal negative 6 or negative 7. Okay.